So you want to do a meta-analysis in Excel, huh? All right, well, here's what you're going to need. You're going to need effect sizes, you're going to need variances, and of course, a good old-fashioned spreadsheet. I mean, sure, it's not elegant or fancy, but it'll get the job done if your goal is to just do a fixed effect meta-analysis, a homogeneity test, and then finally a random effects meta-analysis, which is the gold standard. And so let's just jump into Excel right now and look at this data set that I got. This, again, is from Hedges and Oak in 1985 at Table 8. We have our effect sizes, which are Hedges D's. These are standardized mean differences. Each one of these rows is a different study outcome. So we have a publication 1, publication 2, publication 3. And then each one of these effect sizes, D effect sizes, we have a variance. And this column is absolutely crucial to do meta-analysis with. It's part of the weighting. If you do not have variances with your effect sizes, you need to go back and figure those out. Otherwise, I can't help you because you will not be doing a meta-analysis. And our goal, our aspirational goal, should always be to make high-quality syntheses. And the bare minimum is to have the weighted part to your meta-analysis. So what we're going to do is add 4 columns to these data, and then we're going to take the sums of all these columns, and with the sums is what we're actually going to do all the fixed effect and the homogeneity tests and the random effects meta-analysis. It is straightforward. I'm going to go by as quickly as I can. I have the equation here for the first one, which is the weighted average. And we're going to create 2 columns based on this equation here. The weighted average has the inverse variance, that's the weight, and then also has the effect sizes divided by the variances. And when you divide the sum of those two across your effect sizes, you actually get a weighted average, a pooled mean, or here what we'll call is the pooled D. So the first one is we want to take the weights, and then we want our effect sizes divided by the weights. Let me quickly do that. We got our weight, and now we got our effect divided by our weight. There we go. With these 2 columns here, we could do a standard vanilla fixed effect meta-analysis. And so we're going to take the sums of these, just doing some slight formatting here to make things look nice. We're going to take the sums of those columns, and with these 2 sums, based on this equation here, we could actually estimate the pooled effect, the random effect, the fixed effect meta-analysis. Whew. All right. Fixed effect pooled D, also known as the weighted mean. And the equation essentially is just this column here divided by that column. There we go. We have officially our first results from our fixed effect meta-analysis, which is the average, the weighted mean across all effects. And here it's 0.01, not incredibly big. I'm going to just simplify things for myself right now because I want to present this in a way where I can report it in a study. So I'm just going to round it to 3 decimal places, which is the typical amount that you want to round things for a pooled effect. Okay, so the next goal now is to estimate the variance of the pooled effect. And this is going to be used to estimate the 95% confidence intervals, which are crucial to assess whether or not the pooled effect is non-zero. And the equation here is straightforward. We already calculated the column for this. It's the inverse of the sums of all the weights. There we go. We got the variance of the pooled effect. So now let's quickly convert that variance into 95% confidence intervals. We're going to start with the lower confidence interval. Let me just clean this up here, make it look nice for you guys. Okay, lower confidence interval, then we want the upper confidence interval. And if this bound overlaps with 0, that means there's really no evidence to conclude that this effect is non-zero. And we'll begin with the lower confidence interval. So we take our pooled effect, and we're going to remove the lower bound of the confidence interval. For that, we're going to use the standard normal deviate, 1.96, which is something that's always used. Nothing unusual. Now we want to convert the variances into standard deviations. So we're going to take the square root of the variance we already calculated. So there's our lower confidence interval. Now we just want to repeat the thing again. For the upper bound, 1.96 times the square root of the variance of the pooled effect. There we go. So now we have our nice confidence intervals. We're going to round these up also. And we could report this fairly straightforwardly in a manuscript. What we didn't do yet is figure out what K is. K is the sample size of meta-analysis. N is typically used for representing the sample sizes within studies. K is the sample size among studies. And it's essentially just the number of effects that we included in our weighted regressions. So here we got 18. All right, so let's report the fixed effect quickly. I mean, there's nothing much to it. I will say fixed effect, we want the pooled D, and that equals the rounded value. And then we're going to report the 95% confidence intervals, the lower bound, then the upper bound, then the upper bound, oof, like that, and then it's always good practice to report the number of effects, which is the K, along with your pooled effect. And that's it. Let me just center this so you can see. Squish some of these things around. There we go. So this is how you would report the results from the fixed effect weighted regression. We got fixed effect, pool D, we got the value, we got the confidence interval, and then we got our K. All right, so now we want to move on to our second goal, which is the homogeneity test. This is to evaluate whether or not there's variability in among our effect sizes. Historically, this was kind of used to make an assessment of whether or not you should move on to the random effects. Now the default is to just assume random effects, and nobody reports fixed effects meta-analyses. But because we're doing this in Excel, we got to build upon that model, and making the homogeneity test is useful because we're going to use it to estimate our random effects model. So what do we need for our homogeneity test? Well, we have our inverse variances already, but we're going to need a new column, which is the squared effect sizes divided by the variances. And since, let me just quickly code that up. I think I could just take a shortcut here and make use of the columns that we already estimated. Whoops, I do not want all that mumbo jumbo. And then we want the sums of this column. Again. There we go. So now we could move on to our homogeneity test, which is just pulling together all the sums in this equation. Homogeneity test is usually represented as a Q. And so let's just write up this equation here. We got that minus, oops, I forgot one column. We need an additional column. Whoops. Okay, which is the, oh, no. What am I talking about? I got all that stuff. Okay, so we take the square root of the effect sizes divided by the variances, and you subtract the square. I like to overly use brackets in Excel. We divide it by the sums of the weights, and then finally we include the ratio between effect sizes and variances. I messed up this equation somehow. Yes. There we go. All right. Does that jive with what I got? Sure does. Okay. So the homogeneity test itself is not useful to just evaluate, so we're going to quickly calculate a p-value for that. And the homogeneity test, the Q-test, has a chi-square distribution of k minus 1 degrees of freedom. And so I think that's easy to do in Excel. It's just a chi-dist. And then we're going to take our Q. We're going to take our k minus 1. And then we want it cumulative. And there we go. We got our equation. So this indicates that there is not significant heterogeneity amongst our effect sizes. That's an unusual outcome in my books, but because we're just using an example data set, what can we do about it? And nonetheless, we're still going to follow through with our random effects meta-analysis. We're not going to stop analyses just because of this test. There's many things that could impact the strength and power of this test. And again, the default should be to do a random effects meta-analysis and not necessarily a fixed effect one. All right, so we got a homogeneity test. Maybe we could, I could quickly report this finding. I'm just going to concatenate a string here again for fun. Q, we want to report the value. Maybe I should have rounded it. We're going to round the Q to 1 decimal place, and then we're going to round the P to that. All right. I'm talking way too much. So we want our Q nicely rounded. Then we want to report our degrees of freedom, which again is k minus 1. And then finally, we want to report our p-value, there we go. So that's how we would report the homogeneity test in a manuscript. Let me just highlight these a different color so you could see what we would typically report. All right, so the last part now is to finally do the last thing I promised, which is the random effects meta-analysis. We're going to make use of a lot of these columns and these sums again to estimate that. Here we're going to use the Dursimonian layered estimator for the random effects between study variance component, also known as tau squared, mostly because it's fairly straightforward and it makes use of our homogeneity test. I feel like that at this point there's like 20 of these estimators out there. This is not the fanciest, but it gets the job done. And in our case, this is often the most commonly used between study variance estimator out there. So like, let's use it. And since we're in Excel, we're not going to be doing any fancy optimization, maximum likelihood REML stuff. And so we're just going to stick with the good old-fashioned DL, Dursimonian layered approach. Let me just edit some of these to indicate what we're done. We did a random effects. So first, before we get to the random effects, we need to estimate the between study variance, right? Also known as, like I said before, the tau squared. And we're just going to make use of this equation. It's the only equation with a conditional here. And what happens with the Dursimonian layered estimator is sometimes under some conditions it gets a negative value, and we don't want a negative variance. That just does not make any sense. And so if it ever ends up being negative, we just default it to it being 0. And so we have, I think we have all these components here except for the squared variance. So we need to add a new column, which is fairly easy one. It's the square root of all the weights. Make use of the column that we already estimated. And again, we're going to use the sum of this thing. All right, we're almost done. Okay, so now we just got to pull together this nasty equation. What can you do? So we're going to take the max. And now we're going to throw in the equation. The first part of it is making use of our homogeneity test minus the degrees of freedom, which is k minus 1. And then we have another component, which is the sum of all the weights minus the sum of all the squared weights that we just calculated divided by the sum of the weights again. And there we go. We got our between study variance component. It looks all right. I'm going to round it again. And so now with that, we could estimate our random effects component, because what we do is we take this between study variance tau squared and we add it to all the weights. And then we just repeat these columns. We don't need to repeat all the columns because we're not going to be estimating any other stats other than the random effects component. So now I'm just going to create a new weight, which is the inverse var d plus the tau squared. That is way too long for me to write in Excel. Let me center that just for fun. There we go. All right, 1 divided by... Now we just want to add up our variances. We got that. Nope. Snag our original variance, plus we want to add to it this random between study random effects variance that we estimated. Since it's a constant, we're going to fix that variable. Okay, and then we want to standardize our effect sizes again, but with the tau squared. Let me just quickly modify that here so you could see things. Got to stretch out these columns so you could see the two things that we're going to estimate. All right, so all right, this is it. So we are reaching the end of the video here. I'm going to take the sums of these columns. And so again, we're going to recycle these equations. To get the random effects component, we're going to divide the sum of this part versus the sum of all the weights. And there we go, we got our pooled effect. Let's round it off. Variance, again, fairly straightforward. It's just the inverse of the sum of the weights. Round, and then I'm just going to copy and paste these equations for the confidence intervals here, and that should be it. All right, so we completed our random effects model, classic meta-analysis, all in Excel. I'm just going to modify this reporting string to say that we did a random effects and slightly change these numbers here. I should be using the rounded versions of this stuff, but I'll quickly plug that in later, and then the case stays the same. And now we want to just kind of be thorough in our reporting and report the tau squared also. And then there you go. There we have it. This was kind of like a roundabout way to do a meta-analysis. It's fun doing it this way because, you know, you're reminded of some of the fundamental statistical aspects of how these things are computed. And you get an idea of what people used to do, you know, 30 years ago when they wanted to do their meta-analyses. So overall, you know, we couldn't conclude that there's a significant non-zero effect from these data. And I think let's go back to our goals. Again, just a reminder, we estimated the fixed effect. We estimated the homogeneity test, which we then used to compute our random effects using the Thur-Simonian layered estimator. I mean, this video took way longer than it should have. If you like it, that's cool. I probably do a bit more of these at some point. Doing a synthesis with spreadsheets, which is kind of like I know a lot of people are doing this stuff out there, and so hopefully I could elevate the quality and standards of what they're achieving. But um, if you're really doing a meta-analysis in a spreadsheet, I mean, I feel like you should at least aim for something that is more robust statistically. Look into R. There's a lot of great tools for you to do a meta-analysis. But in a pinch, I guess Excel works, right? Excel gets the job done. All right. Take it easy.